Hi. Very often we are going to have to work with mixtures of gases inside the problems that we're working through. And when we have to do that, we have to know how to treat those individual gases as part of the mixture that they are. And so in order to do that, we're going to have to look back at something that John Dalton said a while ago, many years ago. And he said that the total pressure of a mixture of gases is equal to the sum of the pressure that each gas would exert if it were present alone. And this came to be known as Dalton's law of partial pressures. And mathematically, when it came out and when we started using it, this is what it actually looks like. What he found is that the pressure total of a mixture of gases is going to equal the pressure that gas 1 exerts plus the pressure that gas 2 exerts plus the pressure that gas 3 exerts plus ... Okay, so this ... means that if we have more than 3 gases, we just keep adding up their pressures until we get the total number of gases in that mixture. Okay. Essentially what happens is that the gases and their pressures are independent of each other in that mixture. Okay, so if we have a whole bunch of different gases present together in one sample container, what we're really seeing is we're seeing that we have sort of an independent collection of each of those gases in that same container. None of those gases really interact very often. None of those gases really do much together. And in fact, they all pretty much believe that they have their own, that volume to themselves because of the particles not interacting. And so what we do is we just kind of treat everything as their own sort of thing and hope that those pressures add up, and they do add up. That's just what that says. But we treat all those gases independently of one another. So they're independent. If these gases obey ideal gas law, we can do a substitution to try and throw some other stuff at it and have another mathematical equation to get through this. And what we would say is after this substitution, we derive this equation. And so what it says is that the pressure total is going to equal the number of moles of gas, N1 plus N2 plus N3 plus ... times RT, so universal gas constant, times T divided by V. Now that whole mess equals the moles total times RT over V. Okay, and so the way this is going to work is we can actually figure out this number of moles. We can add up the total number of moles of each of the gases, and we can say that moles total is going to give us pressure total by substituting it into ideal gas law. And that's really what this is doing. And so once you figure out this trick here where we're pressure 1 P2 plus P3 equals P total, it's really not a hard step, and it isn't really that difficult to handle. And so let's work through a problem. Let's see how it goes, and we'll get this taken care of very quickly. Alright, so let's get to the next page here, and here's the example that we're going to work through together. So we're going to talk about a mixture of gases today. We're going to talk about 8 grams of oxygen and 12 grams of methane, CH4, are put into a 19-liter container. So this is going to be, I'm going to call oxygen gas 1. So this is my gas 1. We're going to say that methane is my gas 2. And I have a volume right here, 19 liters, and I went through it instead of underlining it. That's funny. And I have a temperature here. And we want to know the total pressure of this system. Okay. Now, so things that we're going to use. We're going to use pressure volume, ideal gas law. PV equals nRT. We're going to use pressure total is going to equal pressure 1 plus pressure 2 of those gases. And so in order to do that, you'll notice that this is in moles. And so N is equal to moles. And so I was kind of mean and I gave this to us in grams. And so we have to convert those grams of gases first into moles of gases so that we can do what we're about to do. Okay, so here we go. Let's do that. So we're going to start with our 0.00 grams of oxygen over 1. We know that 1 mole of O2 has a mass. We look it up, we add it up, it's 31.9988. 31.9988 grams of O2. Grams cancels, leaves behind moles of O2. We end up with 0.250 moles of O2. Okay. Now, we need to find moles of methane. Do the exact same calculation. We're going to take 12.0 grams of CH4 over 1. We know that 1 mole of CH4 has a mass. It's going to be 1 carbon, 12.0108, plus 4 hydrogens, which is 1.00695. My brain just lost it for a second there. I got 16.0426 grams of CH4. And yes, we could have rounded that to sig figs, but I like to round at the end if I round at all. And here we go. So 12 divided by 16 gives me about 0.748 moles of CH4. Okay, so now we have our moles. Now we need to find our partial pressure of oxygen, and we need to find our partial pressure of CH4. The way that we do that is we just use ideal gas law. And so I'm going to take ideal gas law, PV equals nRT. I want to have pressure by itself. So to have pressure by itself, I'm going to divide both sides by volume. Volume goes away, so pressure is going to equal moles times R times temperature divided by my volume. Okay, and we're going to do that for both of these moles of gas. Okay, the only other thing I have to do before we can actually start doing this math is we have to make our temperature, the temperature scale in Kelvin. And so 0 plus 273.15, this is 273.15 K. All right, so we're good there. So let's just start putting our pieces in and get our pressures. All right, so partial pressure of oxygen, PO2. It's going to equal N, the number of moles of O2. We figured that to be 0.250, so 0.250 moles of O2. I'm going to multiply that by R. Make that a darker line. Sorry. R is 0.08206 liters times atmospheres divided by mole times K. Okay. And the last thing we got to do is we got to put our temperature in. This is 273.15 K. We divide that by the total volume. Total volume for the oxygen is going to be 19 liters. So 19 liters. Okay. If we cancel off our units, liters cancel, moles cancel, moles cancel, K cancels, K cancels. We end up with atmospheres by themselves. And so my pressure of my oxygen comes out to be 0.295 atmospheres. Okay, so that is my pressure of my oxygen. Now we're going to do the same thing with our pressure of our CH4. I'm going to try and write a little smaller because I apparently have given myself not enough space. So PCH4 is going to equal its number of moles, which is 0.748. So 0.748 moles, 0.08206 liters atmosphere, mole K. Temperature is 273.15 K. We're going to divide all of that by the same 19 liters. And in this case, 0.748 times 0.08206 times 273.15. Enter. Divide that by 19. We get 0.882 atmospheres because of the pressure of CH4, or that is the pressure that the CH4 would exert inside that container. Now, pressure total for this system, that's the last thing we want to do. We want to find that the pressure total inside this is going to equal the pressure of the O2 plus the pressure of the CH4. And so all we have to do is add them up, because that's what happens. That's what Dalton's law tells us, is that the partial pressures of each one add up to give the total pressure of the system inside. P of O2 we figured was 0.295 atmospheres, plus P of methane, 0.882 0.882 atmospheres. Make that a little easier to see. So 0.295 plus 0.882, the number that we get here is 1.177 atmospheres of pressure inside that 19-liter container. And so figuring out how Dalton's law works, it's actually not horrible. It just requires a little bit of thinking to make sure that we know exactly what it is we're doing. So there we go. Talk to you again soon.